long haul to the end. We've been watching all the students today. You probably have 2 in your classes, and it's just dead. Yeah, I don't blame you. This has been more of a Monday than normal. But welcome back. I'm glad you're here. We'll have fun the rest of the way. What do we got left? We have, this week we'll finish fluids, gases, and heat. So we'll finish up the heat stuff. Review Wednesday. Have a test on it Friday. And then we'll start waves and oscillations. We'll discuss sound and light some, so you can experience that. That'll be another unit, and we'll have a test on that. And then after that, we'll cram in a little electricity right at the end. You won't have a special test just on that, because then we run out of class. So it'll go on the final with everything else. So we'll cover what we cover of that. And if it's not much, so be it. But that way you can learn some more about electricity. Did you guys have any questions over break? Yeah.
So many. Right.
You had so many?
Yeah, I have a question. So I went to California, and just outside of Las Vegas, they have it's like a big solar panel plant. I don't know if you've ever seen it. So they have like all these solar panels, and they're like 3 or 4 towers. They like trap light and heat and all this stuff. And around the solar panels, or around like the towers, they were like glowing. There were like clouds around it. And I was just kind of wondering.
So solar power plant.
Yeah, I have a picture of
Trap.
it.
There's towers, and the towers were glowing. Yeah, I don't have an answer at the moment.
It's pretty weird. But I was wondering if it had anything.
Glowing. I'm just shooting in the dark here at first. Maybe they heat up, thus transfer internal energy to the surrounding air, which could cause some moisture, some evaporation, and maybe it could cause a little cloud.
Like white glowing clouds that sit around them.
Well, they'll be. I'll have to look into that. And just on the sides, are those reflectors at the top? They're really shiny at the top, or
yeah,
just?
I don't like. That's where I think they trap all the energy.
Well, it's got to have something to do with heat if it's making the condensation there.
Yeah, it's pretty weird.
When if you got water vapor in the air, and that vapor expands, then it's cooling. We discussed that right at the end last time. As air expands, think of convection. As it goes up, it expands, and that allows it to cool off, because all the particles don't run into each other as much. And if it cools off, that means it's losing internal energy. It's dropping its temperature. If it drops enough, it can change phase. The water vapor can condense out, and you'd see a cloud. That's what a cloud is. Here you can watch it as it comes along and it goes up the mountain. It goes up, expands. There's less pressure up there. It expands for that reason too, which cools it. Water vapor condenses out, and you get clouds. You often see clouds going up the side of a mountain. That's why there's lots of clouds over the mountains. And then you get over on the other side in Colorado, down the slope, and the clouds can go away. So it's got to have something to do with that internal energy, and that's obviously going to get really hot if it's trying to focus and collect the... So that's my best guess at the moment. You can keep asking questions, but that applies to this that I was going to show you. So I'm just going to do it. This is a 2-liter bottle I emptied out, and this is a liquid crystal temperature strip. It changes colors with temperature. You've probably seen them on the side of aquariums. How they tell you? That's what those are. They are. They're liquid crystals. They just change their orientation with temperature, so they reflect light differently. So right now it's colder than it reacts, so it's black. It'll change through colors, and if it gets too hot, it'll turn black again. So the idea is if I do work by pumping air into it, I'm compressing the air. You can't all see me, huh? Because someone sat over there. So another excuse to stand on the table, huh? So if you force air in, what happens to the density of the air inside? It increases. Where's this energy coming from? I'm giving the air molecules inside. The lack of breakfast I ate this morning. Chemical energy. So I'm doing work, force over a distance, right? I compress the air, I push it in. And you can see if you cram more and more particles into the fixed volume, it gets a lot tighter. And you can see some color, or at least I can. Can you guys? So yeah, it's heating up. So when air compresses, it heats up. The faster I go, less time it has to come to equilibrium in the room. Okay, I'll stop. So let's take this off. Wow, that's turgid. Now the fun part, if I let the air back out, which I can do more quickly than I can put the air back in, we can watch the temperature change again. Ready? You see that condensation? And you can see the temperature change on the liquid crystal temperature strip. Turns back, cools back off. So as it expands, it cools, and you get condensation. This transfer of internal energy around, because of differences in pressure, is our weather. It's our climate. It's cool. Yeah. Okay. Do you have other questions then? You want to ask? Well, then I got some for you. Clicker time. We'll review a few things we did last lecture. See, you already asked this one. You might as well get a point for it, right? Oh, yeah, it's a little low. Thank you, Ron. Is that better? Yeah. So as you log in and do it, polling's open. Well, I hope you get this right since we just discussed it. Say, I planned this last week. Yeah, I'll ask this one, and this one. We already reviewed this. See if people holler. I'm giving you time to log in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, we have 28 players today. All right. Half of you answered B and a third of you A. Okay. So I'm considering that I failed. Or it's definitely Monday. All right, this one I'll let you talk to your neighbor. Because some of you are getting it, some of you are not. Based on what we just discussed, talk with your neighbor and re-answer. I'll open the polling back up. And let's see if we can straighten some of you out. You didn't miss it, did you?
No.
Find out real soon, right? I have to admit, this is one reason why I like clickers. Because I feel like, the book discusses this. I discussed it. We did a demo. And yet, obviously, it's still not sunk in. So, it shows me that. All right, you voted? 10, 9, 8, 7, 6, 5, 4, 3, 2. 2 people don't want to play anymore. All right, fine. Well, now we have more on B. Good. So, help you understand, those of you that answered A. What's your thought process? When air rapidly expands, it generally warms. Help me help you. so you don't miss it on the test.
So when you pumped air into the bottle, you made it more dense. Was that expanding it when you pumped air in?
What does expand mean?
It's more volume?
Yeah, more volume. This volume is fixed.
Oh.
So pumping air in, we crammed more and more air into the same space. So that's actually compressing.
Okay.
It became more dense, more air in the same space. That's when it warmed, going in, compressing. When I let the air out, it was free to expand. Come out into here. Air left. So there's less air inside. It expanded. And that's when we saw it cool. Okay. Well, maybe now you'll never forget again, right? Let's try another one then. All right, we just started this, but this is what we're going to continue with today. And if you've read chapter 16, this should be a no-brainer, but 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, most of you think both, but a few of you think just the sun. Go ahead and give you the answer. It is both, which is the point of asking this question. Anything that has a temperature gives off radiant energy. It might not be in the visible range where we can see it. And the sun is a lot hotter than the earth. That's why people, oh yeah, it's glowing. Sure, it gives off energy. Well, so does the earth. They're just longer wavelengths. And that we'll discuss more today. They're longer wavelengths. They're not in the visible range, so we don't see a glow come off of it. But there is warmth coming off the earth. There's warmth coming off of you. You know, you can feel it. We give off radiant energy. It's not as high of energy as that comes off the sun or a glowing light bulb, but we still give off energy. Anything with a temperature will give off radiant energy. And I think I had one more. All right, how does that energy get to us from the sun? We talked about the three methods of heat transfer: conduction, convection, and radiation. Which of those does this internal energy transfer from the sun to us? How? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, that's what I expected. C and D. Do you guys want to discuss it again, or just let me give you the answer? Not in a talkative mood today, are you? It's radiation. Only. So, you can put your clickers away. Turn the lights on. The three methods. Conduction. That's where things are in physical contact. The earth is not in physical contact with the sun, so that one's out. The particles in this hand can see particles in this hand, and they can bounce into them, right? And things that are hotter, they're moving around more. They got a greater average translational kinetic energy, so they transfer that energy directly. That's conduction. Convection is through fluid, like air or water. It can heat up, and then hot air is less dense, so it rises up. There's a buoyant force because it displaces enough air around it to be buoyed up. Then we just discussed, as it goes up, it expands and cools and comes down. So convection, you need some medium to transfer the heat around. In water, boiling your water in the pot, or a radiator in your room. Well, there's nothing in between Earth and the sun. It's empty space mostly. So convection can't occur either. Radiation does not need a medium. It just radiates out. You give off electromagnetic radiation. So that's what the sun does. That's what you feel from a hot fire. It just radiates its energy directly to you. It doesn't need the air to do so. Remember popping that firecracker? That was radiation. We focused it onto the match head. Does that help? So let's do this guy. Here's a light bulb. Send electricity through it. Send more through. And I want you to know color differences. When it's hotter, what color does it look? White? I heard? Okay, what if it's cooler? Does it seem to change color, or is it still white? More orange-red, I'm hearing? Well, here, pass these around. We're going to borrow these. These are diffraction gratings. You just need one per person. Pass those around. When you have them, we'll look at the light bulb through that and do it a little differently. Because what I want to teach you is the radiant energy that this gives off, the light you see, is directly proportional to its temperature. It's really cool. You can tell the temperature of stars this way by their color. They are radiating energy in the visible range, and things that are on the blue side of the spectrum have shorter waves. I don't expect you to know this already, but the rainbow, things on the blue-purple side have shorter waves. They're vibrating more quickly. They have a higher frequency because they're vibrating more quickly. And to do that, they make shorter waves. They have more energy. The red side have longer wavelengths because they're vibrating more slowly. They have less energy. So red, less energy, blue, higher energy. So if you saw a blue star, what's that tell you about its temperature? It's hotter than a red star.
So yeah, this weekend me and my friends were having a discussion. That's why Venus twinkles, right? If you look at Venus, it's extremely hot, and that's why it looks blue, whereas Mars is solid, just boring kind of red. And they were saying no, they're saying that's wrong because they say planets can't twinkle.
Planets
can't
can't.
have that luminescent red. And I was arguing no, they can. They just have to be hot.
So you have the color difference between Venus and Mars and whether they twinkle or not. Unfortunately, it has nothing to do with their radiant energy. But since we're on it then, we'll get to discuss this in the optics part. But briefly, Mars has a lot of iron in it. You know, when things rust, they kind of turn a red-brown. I mean, that's kind of a main reason why Mars looks redder. It's because it has a lot of red dust. Venus is hotter due to a greenhouse effect, which I am going to do today. This is 2 thermometers, 1 and number 2 stuck in this container, which I just covered. It's insulated, but I'm going to let light in. This is like Venus. Its atmosphere traps gases. So right now, they're both at about the same temperature. This is in Celsius. So as we continue on, and I come back to this because this takes a while anyway, I'm going to turn on this light, which gives off radiant energy based on its temperature. It's like a 300-watt bulb, so it gets pretty hot. And so both thermometers are going to absorb that energy. This one is like trapped in an atmosphere. It's like Venus. It's a really thick atmosphere. I don't want that. I want this. And so as that works along, we'll see what happens. Ultimately, I think you can guess, it's going to get hotter. So it does have a higher temperature than Mars. And that in and by itself means it gives off more radiant energy. However, it's not hot enough to glow visibly like the sun. So that's not the light we see. But if you hit it with like an infrared camera, if you could see, it would be glowing a lot brighter. So back to the twinkling part. More than you wanted here. Point light sources like stars, when they go through our turbulent atmosphere, the atmosphere. Do you remember when I projected a light source on that heat lamp and we saw convection? Because the hot air went up and it distorted the light ray, the light trying to go through it, and we could see it on the screen. That's the idea of why stars twinkle. As they go through the turbulent atmosphere, they get bent and they look like they twinkle. Something that's bigger, like Venus, because it's a lot closer, I mean, I'm exaggerating. A star looks like a point, little prick, where Venus is actually fairly big compared to the star from our perspective. And so the light from one side of it gets disturbed and twinkles, but so does the light from every other point, and they all kind of overlap and wash each other out. So generally we don't see planets twinkle much, but if they were really far away and small, more like point little dots, it would twinkle. So it's just the light getting bent around through our atmosphere. Waves can bend, and that will be the beginning of our next unit next week. Sound waves, water waves, light waves. As they go through and change mediums from hot to cold or air to water or whatever, they can bend. Does that help? So, everybody's got glasses now. Well, you can see it enough. That one's just kind of distracting. Let's see. That's not even bright enough to see. Let's turn her up a little. And I'd like you to look at the filament. Let's do this one. And off to the side, you should see a rainbow spectrum, do you? Yeah. Good. Those are the visible colors of light that this gives off. These are called diffraction gratings, and when the waves of light go through these little openings in the what you're looking through, they bend. It's another way it can bend. It's called diffraction. And each color, because it has a different wavelength, different frequency, different energy, they get bent different amounts. And so it allows you to see the whole spectrum visibly that's there. Red, again, is the longer wavelengths, less energy. Blue is the higher energy, shorter wavelengths. So, when it's really hot, what colors do you see? Let's crank it all the way up. What colors do you see? All of them. We'll simplify. Red, green, and blue. Yeah, they all seem to be there, right? So this is giving off red, green, and blue. All of them. Which one corresponds to a higher temperature? Blue. Well, that's in there. It's hot, but it's also giving off the colder red, and they're all there. So without the glasses, the filament looks white. A white star would be even hotter than just a blue star, because blue would only give off the high ones. It wouldn't have all the low ones. This one has it all, right? If I turn it back down a little, watch. Keep looking through your glasses. Tell me what happens to the blue. That purple end. It's shrinking. Good. I hope you see that. Tell me if it disappears. Can you still see red and green? That's the idea. So this is not as hot, because the blue part's out of the spectrum. And you can visibly see, oh yeah, it looks redder, oranger. Red and green together mixed to make yellow. If you add more red than the green, it looks more orange. So spectroscopy, this is called. Spectroscopy, if any of you have heard of that. And that's how astronomers can tell what temperature different stars are. So the key concept here is temperature is directly proportional to the radiant energy. The peak frequency that comes off is directly proportional to radiant energy. So you can tell something's temperature by that radiant energy that comes off. I think that's cool. All right. Okay, turn that off. Turn the lights back on. You can recollect those glasses and send them back the other way. You guys have any infrared thermometers? They're way more popular now. They have them at the hospitals and for infants because they're instant. This one, well, let's turn the laser on. It's more fun. There it is. So what it does is there's a little computer chip in there, if you will, sensor, and basically you're giving off radiant energy. Everything is. It goes into here. This can focus into it opens into a cone. So it'll detect everything, If I'm here, it's detecting everything there. If I get closer, I can get just your head. I'll turn the laser off. The laser was not off. There we go. And it's reading 32 degrees Celsius. But I'm sure it's getting more than his head. How about the chair? 23. Yeah, about room temperature. 23. How about the wood? 23, the metal. 23, see, the wood and the metal are the same temperature. But the IR thermometers, infrared, work because they're just detecting the radiant energy things give off. And if things are hotter, it can tell. Let's do the light bulb. I can't see. 200 degrees Celsius, that light bulb's at. Let's see what's happening over here. Oh, you can tell already. The foam box, Venus, if you will, is a higher temperature. So what's going on there? This is the greenhouse effect. I bet most of you have heard of it. We get to understand it better. Thank you very much. So one is you can actually build an actual greenhouse where you have plants in it, right? You can think of your automobile with all the windows up on a hot summer day. Think of planet Venus. Think of Earth with its atmosphere. It happens too. We're just not as bad as Venus. So the radiant energy comes from the sun. And it's really hot. So what kind of waves? Shorter waves. Yeah, shorter waves. And they can get through our atmosphere and through the plastic, through the glass, into the car. Where do those waves go then next? They bounce around forever? Do they escape? Do they just keep bouncing forever? What if you're sitting in your car? What do you notice? It gets hotter. So you're actually absorbing that radiation, the energy, like the match head. You absorb it. And so your temperature goes up. But you're not as hot as the sun, right? So what kind of waves do you give off? Not short, but longer. And they can't escape. They can't make it through glass. Glass is transparent to us visibly, in the visible range. But they let short waves through, but not long waves through. So the radiant energy from the bulb or the sun can get in. Heats up what's inside. They give off their own radiant energy, right? But it's less, longer waves. And they can't make it back out. So they're trapped. And that's why it heats up. It's the greenhouse effect. And that's a significant difference. So the left side's nearly at 40 degrees, and the right side's barely above room temperature at 24, 25 degrees. Does that make sense? We'll see how hot it gets. Let it keep going. All right. Did that. Well, there's really only 2 more concepts in this chapter. And we've already discussed one. They just gave it a name. Newton's law of cooling. Did you guys read about that? Newton's law of cooling. Basically, it just says what we already know. They gave it a name. Heat was proportional to what things? What determined how much heat something took or absorbed or gave off? Do you remember? Difference in temperature, right. So it's proportional to a change in temperature. The greater that change, the more heat will be transferred from hot to cold. Yeah, the rate. Exactly. Goes faster. And that is Newton's law of cooling. They gave it a name. Same Newton. So basically it just means if you want to cool something off quicker, lower its temperature, you stick it in the refrigerator, right? Because there's a bigger temperature difference between the hot object and the cold refrigerator. If you want to do it even faster, make a bigger temperature difference. Stick it in the freezer. And the greater that difference, the faster the rate of change. The faster internal energy transfers. That's what heat is, energy in transit. Now, as the thing, as your leftovers, right, they're hot, as they cool, there's less and less difference between it and the refrigerator, right? So the rate slows down. But initially, it's going to start cooling off a lot quicker than if you just leave it out in the room. Hopefully this makes common sense to you guys. But it applies to everything. What else is heat transfer proportional to? Mass, good. You got more of something? Well, it's going to take, if you're trying to heat it up, you have to transfer more internal energy into it to have the same rise in temperature. Because you got more of it to share it. What else? There's one more. Yeah, specific heat capacity. And that's the type of material. What has a really high specific heat capacity? Water. So it has a high thermal inertia, resistance to wanting to change. So it's going to take more to have the same change as something with a smaller specific heat capacity. And those were exactly equal. That formula is handy. Anytime there's a temperature change, that defines it. So the Newton's law of cooling is specifically just giving a name to this part. It was a good way to review, right? Since your test is Friday. So the last thing, too, makes a whole lot of sense to me. And that is, what determines whether something gets hot or cold? If everything is giving off radiant energy that has a temperature, why do they not just cool down? I mean, if I'm continually radiating energy off, or this has a temperature, it's giving off radiant energy right now. Why does it not just get colder and colder and colder and colder?
It's also absorbing.
Bingo! It's also absorbing. Everything's in transit. Hardly anything's really at equilibrium. The temperature can stay consistent, like right now it's at room temperature. It's not changing. But realize what's going on. It's giving off radiant energy, so it must be absorbing radiant energy at the same rate. You with me? And if that's balanced, then the temperature doesn't change. It's like equilibrium we had with forces, right? I can push on you, or you can the car can accelerate, right, to propel you forward. But if there's enough wind resistance and friction pushing back on you, you don't change your speed, do you? You can still maintain 55 miles an hour. You can still have the same consistent temperature. But realize what's going on. You're always radiating energy and absorbing at the same time. So how would something in terms of energy, emitting and radiating, how would anything raise its temperature? Yeah. If there's more being absorbed than giving off, then the net effect is you're going to gain more than you give off. That'll cause you to raise your temperature. Or it gets trapped. Yeah, that is what we'd say a net absorber. It's absorbing more radiant energy than it's giving off because it's staying trapped the whole, yeah. And that's how it gets hotter. In the reverse, if something's going to cool off, it's a net emitter, right? Because it has to be radiating and emitting energy more quickly than it's absorbing. And it's just a balance between the two. Do you have a question, Ron?
Well, I think from what I thought, I think I figured out how the refrigerator works. But does it have something to do with, like, they have these freon coils that are so cold, and it's colder than what's inside the refrigerator, so the warmth goes. Is that the?
That's right. Yeah. Let's walk through that. Qualitatively. You put your food in a refrigerator. It's warmer than the surrounding air. Okay, we know which way heat flows, from hot to cold. So the food is radiating its energy, and it's radiating more than it's absorbing because the surroundings are colder. So what happens to it? It cools off. It's losing energy. It's a net emitter. Well, where's that energy going? Because the air in the refrigerator is warming up because it's absorbing. Well, what it does is, that's where the freon coils come in. They come in the back and they're really cold. Well, heat transfers from the warm air into that freon, which is colder. So there we go, back to normal. But now the freon's warmer. So it goes back through a compressor and a pump, and it does this compressing, expanding thing, and it can cool it back off. Okay, that's great. It's cooled. Where does the energy go now? We started with some hot leftovers, right? We transferred it to the cold air in the refrigerator. Then we transferred that warmer, because it warmed up, to the freon. We cooled it back down so it can keep pumping. Where does that internal energy end up? Because you can't just make it disappear, right? Where are the coils at on the refrigerator, Ron?
Well, I know you have like water given off from the refrigerator or something. I don't know if that's from ice melting. Is that condensation?
It's condensation. And we know things condense, when they cool down. That's the warmer air hitting the cold condenser coils, and it pulls water vapor out and makes it condense, because the water vapor gives up its energy and condenses into liquid,
So does
drip, drip.
energy go into that?
Some of it goes in to do that, yes. Okay, and where'd that water vapor come from? Where'd it start at? That was condensed on the coils. Where'd we get that air? The outside. Outside the refrigerator. Feel the back of a refrigerator or underneath it. It's warm. The air right there is warm. So the internal energy that started in your leftovers ends up outside the refrigerator in your room. It has to. Energy is conserved. That's all a refrigerator is. Same with an air conditioner. It's doing the same thing with your air inside, but where does it stick it? Outside. Feel the outside of an air conditioner. It's warm right there. It's heating up the outside. These are heat pumps in a refrigerator. They can work in reverse too. Instead of cooling something down, we can heat it up. Well, that means the reverse happens. And so for your leftovers, they're a net emitter because they're cooling off. But that is one way. I mean, you could, right? You could set up your refrigerator, open up the door in your dorm room, right? I've seen people do this. Close the windows, close your door. Open up your refrigerator because it's a hot summer day. And just let it cool the room, right? Will that work? I mean, the air is cold in a refrigerator. It makes the air cold. If you stand right next to it, you feel cold, right? What will eventually happen, though? If I'm getting colder, what else is happening? The air is getting warmer. The same air in the room we're trying to cool down. It's not going to work. You're just going to make your refrigerator work too hard and fry it out. So you might be cold for a while, but yeah, that heat has to go somewhere. It's going into the room. Maybe if you can vent it outside the window or something. But then you're warming up the outside. But maybe you don't care about that. So it's just this give and take between energy. And we will not be covering the subsequent chapters on thermodynamics, but those of you that are interested or continue on, that's what it's all about. It's conserving energy and deciding where energy goes. Energy naturally flows from hot to cold. If you want to go the other way, you got to do work. You got to supply your own energy to compress the freon in the coils to work the other way. And it says that in doing so, kind of like friction we had, I'm going to slide this. Great, I gave it energy. Well, some of it got wasted by friction, right? Well, the same thing happens with heat pumps in a heat cycle. You put energy in, you can't get all of it out. That's pretty much all thermodynamics is. And there's rules and guides to equation to determine exactly how efficient something can be. But nothing can be 100% efficient because there's always some of this heat that is useless. We can't convert to useful energy. The part in chapter 16 on solar power, I'm not as interested in. It's good reading, but you don't have to stress over it. So, let's review with a thermos here. We have, this is my little thing my daughter got taught in school, make more sense now. We have methods of heat transfer: conduction, convection, radiation. Conduction, convection, radiation. How does a thermos work? This is your review of those methods. Here's a thermos. They keep things that are cold, cold, and they keep things that are warm, warm. So I can put liquid nitrogen in here and it'll last for quite a while. Or I can put my hot chocolate in here and it'll last for a while. Why? It's insulated. Okay, which method does that stop? Conduction, convection, or radiation? Not convection. I heard it, but you guys didn't sound confident. It's conduction. Do you know how they make thermoses? You ever thought about it? What's the insulating material? Do you know? Yeah, most have an air gap. So this thing is double lined. There's like two walls. So it kind of looks like this. Kind of like that. And the space in here, if it was air, that'd be good, because air is a poor conductor of heat. It's a great insulator. So if something's hot in here, hot temperature, then it tries to conduct through the wall, but it doesn't conduct through air well, so that would keep it warm. It would keep the heat in, because it's trying to flow out. And if it was cold, it keeps this heat out, because it's hard to get in. So yeah, insulating is conduction. And good thermoses use a vacuum. They'll evacuate the glass. This one is. It's glass. Can't see. And they evacuate it, so it's a vacuum. So it can't conduct at all through the walls. What else? So they're good for conduction. Think about convection and radiation then. I'll take your not jumping up immediately. That's good. You haven't never thought about this before? I'm shocked. The color does. This is black, but it's on the outside. Right there, it's colored. What would black do? Yeah, it's a good absorber. So it would actually, if we're trying to keep something cool in here, it's absorbing heat. So actually that's not a good thing. While we're on it though, black is a good absorber. It's also a good emitter. If it's easy to absorb, it's easy to give up too. So black will cool down more quickly also. So yeah, that's not good. Can you see here though what color it is inside the walls? Good ones are silver, a lighter color, because they don't absorb. So yeah, the inside of this, and if it's really good, the inside of this would be silver, because they would reflect any radiation back where it came from. So it would keep anything trying to warm it up from getting in, bouncing it off. And if it's hot inside, it would keep it trapped, because it would bounce back in. Which one is that helping? Conduction, convection, or radiation? Radiation. Yeah. Things that are hot radiate. They give off these waves. White and silver reflect it. Just like a mirror reflects visible light. So yeah, being silver helps with radiation. All right, tell me how we stop convection. How's a thermos help with that?
It's made of metal.
It's made of metal. How's that help convection?
Because it's got a low thermal inertia, and so your hand will heat up the metal, but the metal can't really heat up the
So yeah, if let's say this is cold, my hand's hot. If it's metal, it does have a low specific heat capacity, which means it has a low thermal inertia. It can't resist changing its temperature as easily as water. So the internal energy from my hotter hand will transfer to it easily. And so it's actually a good conductor of heat. And so that actually doesn't help. Because you see, we don't want heat to conduct through. Convection. How does convection work?
So it's the lid? Lid on it? Is that why?
It's the lid. Yeah. Boink. Best thing you can do to keep your coffee hot, put a lid on it. I mean, you got a lame cup. They're usually paper cups, right? Or styrofoam. That'd be good, because that insulates, like this. So that would stop conduction. This one has a vacuum or air. So insulating stops conduction. Heat stays in or out. If you put a lid on top, then any convection currents moving in here can't get out. So they can't escape and warm up something else and lose energy, or vice versa. So the best thing for convection is just put a lid on it. For irradiation, this one works great because it's a lighter color and reflective. For your coffee cup, well, if it's white, it's better than black because it would reflect the radiation more.
What causes those convection currents?
As its temperature tries to change, well, that's true. Any fluid will cause it. It's not perfectly uniform all the way through, and if there's one little spot, say these molecules are moving slightly faster at a given moment than these, then there's a temperature difference, locally.
And that's what causes it.
Yeah, and that causes a convection current. Or if this is sitting on the ground, a table, then there's very little conduction going on here, but there might be some, especially with a styrofoam cup. And that'll heat up the bottom, and that'll expand and rise. Cold will come in, and so you'll get some convection. Or just think of air moving in the room. It swings by, right? And when air goes over the top of this, it's moving. What's that do to the pressure here? It lowers it. There's greater pressure inside that will actually pull some of the air out with it. Well, that's going to cool whatever inside. That's causing the fluid to move. That's part of convection. So just putting a lid on it will help that. I like our thermos. It's a good review of all that. See, what's our greenhouse at? 52 degrees, and that's still down there at like 25, 26. So here's my last one. If you read the chapter, you know. But what color is the hole? And does each hole look the same blackness? The center. Of the one, which one is it? This one. I put different materials that are black on there. Which hole, which circle is the darkest, the blackest? You think it's the middle? Well, this one, they're both black. Okay, so you open this one up, and what color is inside? Black. So it makes sense. You open this one up, black hole, darker than any other black. It's white. Huh? So what's going on there? Still black. Still black. What temperature is inside, do you think? What temperature do you think the inner walls are? It should be at room temperature. It's been sitting out here all class. So it's come to equilibrium with the temperature in the room. They're both the same temperature. What determines the wavelength of light radiation given off? Temperature. So they're at the same temperature, so they're giving off the same radiant energy, even though they're different colors. White can reflect visible light better. We're going to talk about that later. But they're the same temperature, so they give off the same radiant energy. If I close them, it's like, are they net emitters or net absorbers? Are they changing temperature? Is one getting hotter or colder? What? If they're net absorbers, they should be getting hotter and hotter, correct? Do you think they're getting hotter and hotter? No. So they're neither a net absorber nor a net emitter because they're not changing temperature. Radiation goes in through the hole and it bounces around in there, right? The material absorbs that. Yes, this is where you're thinking, black is a better absorber. Not a net absorber, but a better absorber. So it will get up to room temperature more quickly than white. But now they're both at room temperature and there's no reason to change, or they're not changing, the same temperature. And whatever radiation goes in, it's bouncing around. It's not getting absorbed, or it's absorbing and radiating at the same rate. We're in equilibrium. And a lot of it gets trapped. So the point here is you see very little of that radiant energy come back out. And it looks dark. They explain this well in your book, so you can review that again, reading that, or we can discuss it next time. We'll review everything next time, gases, fluids, liquids, This heat, more of the heat stuff? Yeah, Ron?